Hello everyone, my name is Tirupattur and welcome to my dissertation defense. The title of my thesis is Video Action Understanding, Action Classification, Temporal Localization and Detection. So we all know that computer vision deals with processing of images and videos to gain a higher level understanding of their contents. And in computer vision, video action understanding is one of a fundamental tasks which involves comprehending the actions performed by humans in videos. Advances in this video action understanding have revolutionized many fields, such as video surveillance, human robotic interaction, sports analysis, and autonomous driving, to name a few. So, central to the task of video understanding are four fundamental questions that are what, when, where, and who. And we will look at each of these in detail. So, the question of what is addressed by the task of action classification. And here the aim is to recognize an action that is in a well-trimmed video without having to do the localization. Here is an example. So given this video, the aim of action classification is to predict the class of action as basketball shooting correctly. The question of when is addressed by the task of temporal action localization. It involves temporally localizing an action in a long untrimmed video. And here is an example. And this task not only addresses the aspects of what, but also the aspect of when. Here is an example video. So given this long untrimmed video, we want to find the temporal boundaries, the start and end time steps for the different action instances. And coming to the question of where, this is addressed by the task of action detection. Here, in addition to spatially, temporally localizing an action, we also have to spatially localize the action. So given a long untrimmed video, we have to spatio-temporally localize an action. And this addresses the aspect of what and when in addition to the aspect of where. Here is an example. So given this video, the aim is to predict the spatial and temporal extents for each of the action instances, here shown in bounding boxes of different colors. And each of the color here corresponds to the class of an action. Finally, coming to the question of who, this is addressed by the aspect, this aspect is addressed by the task of action biometrics. So this is a novel task where we want to recognize or identify a person based on irrespective of the action that they are performing. And this addresses the aspects of both what and who. Here is an example. So if you have a video of like a probe video, which is shown on the left, of a person doing an action, we want to retrieve other videos of the same person doing different, irrespective of the actions that they are performing. So to give you an outline, so in this discussion, we propose approaches to address each of these fundamental questions, which forms the outline of my presentation today. So the first, we will look at our work on multi-view action recognition, addressing the aspect of what. Then we will look at the multi-label temporal action localization work, addressing the aspect of when. Then I present to you our system on real-time action detection, which addresses the aspect of where. And finally, I will present to you my work on action biometrics, which addresses the aspect of who. So the first work is addressing the aspect of what. And so this work is titled DVA-net, Disentangled View and Action, Disentangled View and Action Features for Multi-View Action Recognition. This paper was published in IIII 2024. So as I mentioned, action recognition is a task where we want to classify an action given a trimmed video. In this work specifically, we address the problem of multi-view action recognition. That is, we want to classify an action irrespective of the viewpoint that it is captured from. Here is an example. So we are given these three videos of the same action, which are captured from three different viewpoints, and we want to recognize these actions irrespective of the viewpoint. So the goal here is to learn better representations which can handle this multiple views and give us good performance on action recognition. So the idea that we pursue in this is to leverage the concept of disentangled representation learning. And to motivate the need for disentangled representation learning, I would use the following figure. So assume that we are given these 9 different videos, each of 3 different classes. And for each class, we have 3 different samples captured from 3 different viewpoints. So here the videos are color coded based on the based on the action. And let's say if we extract features from these videos using the pre-trained model, or we train the network on these videos and extract the features, what we would observe is that the features would follow some distribution like this. So these features will be entangled in the sense that the network might learn representations which are specific to the viewpoint rather than the actions. So we want to overcome this. One approach is that we can apply a view invariance loss term while we are training the network, and that would help us separate the samples based on the actions shown as shown here. But that's not enough. What we are proposing in our approach is disentangled representation learning, where we not only separate the samples based on the viewpoint but also on the actions, and we show that this kind of a learning will help us get better performance on multi-view action recognition and also generalize well to unseen viewpoints. So coming to the proposed approach for this task. So given a video, we pass this video through a pre-trained spatiotemporal encoder to extract the features for each of the time steps. So given these features for the individual time steps, we add positional encoding to that and pass it through a transformer decoder block. So in addition to the inputs from the video, the transformer decoder block takes in two sets of learnable queries. One set of learnable queries are for the actions, and one individual learnable query for the viewpoint. So the outputs from the transformer decoder are the refined action queries and the view queries. So if we have A different actions in our data set, we have A refined feature queries. So we average them and to get a one representation for the action, which we pass it through a linear layer to classify the action in the video. So similarly, we take the representation or the refined action query, refined query for the view features and pass it through another MLP layer to classify the viewpoint of the given video. So we have these two classification losses, one on the actions and one on the viewpoint. In addition to these well-known action classification losses, we also introduce this contrastive loss, which help us to do this feature disentanglement. So the first contrastive loss is on the action features. So here the motivation is that if we have two different samples, for example, the anchor shown in blue and the same action video shown in pink, because they are of the same action, we want the representation to be closer in the feature space, and we want to bring them together. And if we have two different videos, like for example, the anchor and the video with same view, even though they are from the same view but of different action, we want them to be farther away in the representation space. So we push them away. So that's the contrastive loss that we apply on the action features, and we apply a similar contrastive loss on the view features. Here, given two samples belong to the same view, we want to pull them together in the representation space. And if there are two samples which are of the same action but from different view, we want to push them away. So here is a formulation for the view contrastive loss and the action contrastive loss. Apart from these four losses, we also add an orthogonality loss on the learnable query tokens that we have, query features that we have for the actions, and we observe that this improves the performance. So overall, the final loss for this training is the combination of all of these losses. Coming to the quantitative results, we evaluate our approach on multiple datasets, and the first dataset that I'm gonna is the NTU RGBD 120 dataset. This is one of the biggest dataset in this for this problem in this domain, and we evaluate our method on two different settings: the cross subject and cross setup. So the cross setup evaluation setup is where we are evaluating the performance of our model in the unseen viewpoints. And on both of these settings, we achieve better performance than the current state of the art. So we also run experiments on a smaller subset of this NTU RGBD, which is NTU RGBD 60. And there also we see the similar trend. And we show similar trend on PKUMD and NUCLA datasets, which are a bit smaller datasets. Coming to the qualitative results, so we want to show the feature disentanglement in action. So what we want to do is that we take the action features, and let's say we are taking the action features for this query video, and if we do retrieval based on these features, we observe that we were able to retrieve samples belonging to the same action irrespective of the viewpoint. Similarly, we did the same visualization of using the view features. So if you take a sample of right view and retrieve the samples based on the view features for that, we retrieve all the samples which are of the right view irrespective of the actions. So this shows that we have learned the feature disentanglement. Apart from that, we also do TSNE visualization on the action features. Here we take 10 different classes and we visualize the features for that. And here is the TSNE visualization of that. So we see that the action features cluster well based on the class labels, and that means it's learning action specific representation. We do the same thing with the view features. And again, we see a clear separation between the samples belonging to different views. Um, Apart from these TSNE visualizations, the final visualization that we have done is that we combine the visualization which has both the action features and the view features. The way that we do it is we take one of the samples from the test set and use it as our reference, and we compute the distance between this sample to every other sample using the action features and also the view features. So the action features are plotted on the right on the x-axis, and the view features are plotted on the y-axis. So when we do this plot, we observe that the relative position of these samples show that the clustering is not only based on the action features but also on the view features, and this ties back to the motivation figure that I have shown you earlier, and this proves that we are learning disentangled representations. So in summary, in this work, we have introduced the network called DVNet, which is a novel network architecture to solve the problem of multi-view action recognition. And we achieve state-of-the-art performance by leveraging this disentangled representation learning. And we achieve competitive results using only the RGB inputs without the need for other modalities. And just to reiterate, this paper was accepted in AAA 2024. So in this chapter, we have looked at the problem of action classification, which is addressing the aspect of what. Next, in the next chapter, we will look at the aspect of when by our method on multi-label temporal action localization. So this paper, titled Modeling Multi-Label Action Dependencies for Temporal Action Localization, was published in CVPR 2021. So the problem that we are trying to solve here is the problem of temporal action localization. As I mentioned, here the input is a long untrimmed video, and the task is to find the action boundaries for the action instances in that video. So here is an example. So given this video, we want to find the start and end time steps of the different actions that are there here. For example, there is running, jumping, and falling. So if you look at these real world videos, what we observe is that there are multiple complex actions that are happening here. And there is an inherent relationship between these actions. For example, you cannot fall unless you jump. And when you're doing pole vaulting, you will run. So based on this observation, the motivation of our work is to model these relationship between actions to improve the localization. So the relationship between actions we categorize into two buckets. So the first one, what we call is co-occurrence. That is two actions that always occur together. And the second one is temporal ordering, where one action follows the other or one action precedes the other. So the example for co-occurrence is the one that I was talking to earlier, which is about running and pole vaulting. So whenever there is a pole vault action, you always have running in it. So this is the example of a co-occurrence. And the example for temporal ordering is this example from basketball. So every time you dunk, you dribble before you dunk. So there is this temporal ordering of actions. So we want to leverage these relationships. So here is the network architecture that we propose to solve this problem of multi-label temporal action localization by learning the relationships. Let me go. It has three main components, and I will explain each one in detail. So the first stage is a feature extraction stage. So given a long untrimmed video, first we divide this video into non-overlapping clips of a certain length. So here we divide the video into T chunks. Each of them is a clip which is non-overlapping with the other. And we pass these clips through a pre-trained backbone. And here we use I3D backbone to extract the features. So after extracting the features, we would have one feature for each of the clips. So you can think of this as we have T clips. So we have a T cross F feature from the pre-trained backbone. So one thing to note here is that we extract the features and start our training. So the pre-trained backbone is never updated, and we don't change the weights there. So the input to our network is actually this T cross F feature vector. So if you see here, the features that we have is only for individual time steps, but there is no concept of class here. So we want to introduce the concept of class-specific features into here. So what we do for that is we pass these features through a fully connected layer to expand the feature dimension. So from F dimensions that we have for each time step, we expand it to C cross H. And we reshape the output into this 3D tensor, which is T cross C cross H. So for every time step, for every class, we have a feature dimension of H now that we can work with. Once we have these features extracted, then we pass these features through our proposed MLAD layer. So this MLAD layer is where we are learning this co-occurrence and temporal relationships. So to do that, we have two different branches in the MLAD layer, which learns these co-occurrence relationships and temporal relationships. I will talk about the MLAD layer next, explaining them in detail. So as I was mentioning, the MLAD layer has two branches. First, let's look at the co-occurrence branch. So in the co-occurrence branch, the idea is that we want to learn the relationship between classes that are occurring together occurring together. That means within both the actions that are occurring within a time step. So what we do here is that we pass this T cross C cross H to the self-attention layer. And in this attention layer, we have T different heads. And in each head, we learn this C cross C attention maps. So with this learnable attention, what we are trying to teach the network is to learn the correlation between the actions that are happening at the same time step. Now the temporal dependency branch is actually a replica of the same of the co-occurrence branch, but here instead of passing T cross C cross H as an input, we permute the inputs and we pass C cross T cross H as an input. Now what we would have is that we would learn these temporal relationships. So we have C different attention heads, and in each attention head, we are learning an attention between across all the time steps. So we have an attention map of T cross T. So with this learnable attention across time steps and across classes, this MLAD layer learns the both co-occurrence and temporal dependencies. So the outputs from both of these branches are combined using a weighted average, and we use a learnable weight parameter to decide how much information that we want to get from each of the branches. So that's how the MLAD layer refines the features. So in our network, we add multiple of these MLAD layers in series so that there is multiple iterations of feature refinement. And at the end, we would end up with the refined features, which is of the same dimensionality as T cross C cross H. Now, given this, we want to classify what actions are happening in each time step. So to do that, we pass these features through to multiple FC layers. So specifically, we have CFC layers, which is classifying each of the classes and predicting the probabilities for each of the class in each of the time steps. So the output from our network will be a T cross C, where T is the number of time steps and C is the number of classes. So, and then we know the ground truth, where we know the ground truth of each of the classes that are occurring in each time step, and we use that to compute the binary cross entropy loss and train the network. So in addition to having the classification loss at the end of the network, we also apply the same classification loss at the beginning before we apply the MLAD layer. And we will show that how that impacts the performance. So that's about the network architecture, but now coming to the evaluation. So as I was mentioning, so there could be multiple actions that could be happening at the same time. So we are looking at evaluating our system to understand how these relationships are learned. But existing multi-label metrics, for example, this Hamming loss, zero loss, and so 0, 1 loss, and so on, they do not capture these relationships because they evaluate each of the classes in each of the time steps individually. So to overcome this, we propose our own metric, which would take into consideration these learned co-occurrence and temporal dependencies and evaluate that. So to do that, consider this traditional precision and recall metrics. So here we are computing the precision and recall for a class C. To extend this to capture co-occurrence dependencies, we propose the extension like this. So we compute precision and recall metrics given that class Ci and class Cj are occurring together. And we look at the instances where they are occurring together and we compute the precision and recall based on that. Similarly, to extend this for temporal dependencies, we introduce the new new thing called tau here. So the tau is a temporal window. So if two classes Ci and Cj are occurring within a temporal window, then we would consider that as if you predict them as occurring within the temporal window, then we consider that as true positive, and then we compute the precision and recall based on this formulation. So both of these metrics help us capture the co-occurrence and temporal dependencies. So here are our results using this proposed metrics on multi-Thomas dataset, and we compare the performance of our method with the previous works using this metric. And when tau equal to 0, that's basically the co-occurrence, and when tau equal to 20, that is the temporal dependence. And in both the scenarios, we observe that our method gets better performance than the previous best methods. In addition to evaluating using our own proposed metric, we also evaluate our method on the traditional FMAP score, which is the frame level MAP score. And we compare the performance of our method on both multi-Thomas and Charades datasets. And we compare with the then state of the art TGM work, and we show that we achieve considerable improvement over the state of the art on both the datasets. Coming to the ablation experiments, here we show multiple ablation experiments for each of the components. So the first one is the number of MLAD layers in our network. What we observe is that as we increase the number of MLAD layers, our performance increases, but after 5, we see that the improvement saturates. Now, the second ablation that we do is the number of clips that we pass in as an input, so the sequence length. So here we see that when we increase the number of clips, the performance increases, and again, it saturates at T equal to 128. The next ablation that we have is using the different modalities. So we evaluate our performance with RGB and flow, and we also do this fusion, and we observe that early fusion of the features gives us the best performance on both the datasets. Then this is the ablation with and without the initial loss that I was talking about. So when we add the initial loss on the features before we apply the MLAD layer, that improves the performance because that nudges the network to learn class specific features before we pass it to the MLAD, and it will help the MLAD layer learn the dependencies between classes. Finally, the ablation on the learnable parameter within the MLAD layer to combine the outputs from both of the branches. And we see that having a learnable parameter gives us a small boost in performance. And we also do the analysis where we check the effect of both the branches in the MLAD layer. So if you use the baseline is where we don't use the MLAD layer, and that's the first row. And if you add the co-occurrence branch and the temporal dependency branch, we see that we have an improvement, but we get the best performance when we add both of them to our network. Apart from getting good results, this network architecture, because it uses self-attention, can also provide some interpretability. So to show that actually the network is learning this co-occurrence, we visualize the attention maps from the co-occurrence branch, and here the attention is across classes. So we have a C cross C attention map. Sorry, there is. Yeah, so we visualize this attention map, C cross C attention map. So what we do this visualization for all the layers. So I'm showing you here the layers from 1, 3, 1, 3, and 5. So what we observe is that at the final layer, we have good attention between those classes which are relevant. So here what we are showing is, instead of showing the attention map for all the C classes, we are showing the attention between a subset of classes. So the class shown in black is the one which is which we are interested in, and the classes shown in green are the ones which are relevant to the class clean and jerk here, and the red ones are irrelevant classes. So when you look at the attention map here, the attention is only between those relevant classes, and this shows that the network is learning the co-occurrence. Similarly, we do the visualization of the attention maps from the temporal branch. Here, the attention maps are T cross T, which is across time steps, and we observe that we observe this checkerboard pattern when we see this attention maps. So what this checkerboard pattern shows us is that there is a high attention between the time steps where the action is happening, and there is no attention between the time steps where there is action and there is no action. So this shows that the temporal dependency branch is actually learning the temporal relationships. Coming to the qualitative results, here is an example where we are comparing the performance of our method and the then state of the art TGM with the ground truth. And what we observe is that the predictions from of our network are more highly correlated with the ground truth than the TGM. So to summarize, in this paper, we propose the MLAD layer, which is a novel network architecture to solve the problem of multi-level temporal action localization. And this MLAD layer achieves state-of-the-art performance on multiple data sets by modeling these co-occurrence and temporal dependencies. And we proposed a evaluation metric to evaluate the performance of these multi-level models. And with this proposed metric actually captures the action dependencies. And finally, to highlight, this paper was accepted in CVPR as an oral. So to recap, we have looked at the first problem of multi-view action recognition, where we are trying to classify an action irrespective of the viewpoint. And then we looked at the problem of temporal action localization, where we are trying to find the temporal boundaries of each of the action instances in a video. So in both these problems, the assumption is that there is only one actor performing one action. It will be multiple action, but there is only one actor in the field of view, and we are trying to classify that. But that assumption doesn't hold in real world. So the work that I'm going to talk about next is the work that is addressing the aspect of where we propose this real-time, real-world action detection system. So the title of the work is Gabriela, an online system for real-time activity detection in untrimmed security videos. So this paper was published in ICPR 2020. So the problem that we are trying to solve here is is to process these untrimmed security videos, and we want to perform spatiotemporal localization of actions. So if you see this video here, there are multiple actions happening. There are interaction between people and so on. So there is a huge field of view, and the region where the activities can be happening is very small. So this introduces a lot of challenges. So coming to the challenges in this approach. So given this video, first it's an untrimmed video, so we have to address that. And there are multiple activities, as I mentioned, and these activities can be of varying length. Some of them can be very short. For example, opening door can be less than a second, but walking and talking on a phone, or vehicle turning right, vehicle turning left, they can be of varying length. And there will be multiple actors involved here. So for example, if you see the example here, there are two people involved in the activity of talking, and these actors not only interact with each other, but there could be interactions between actor and object. So the person is interacting with the bottles there, and she's setting up the bottles. And we have to also model these interactions. And finally, one other aspect is that there could be multiple scales involved here. So there could be, for example, if you see there is a car, going at the very far end of the camera, far end of the video, where the motion is, I mean, you see that the car is very small, and we have to recognize that action. Apart from that, there could be also imbalance in the data set. There are some classes are very frequent and others are not, so we need to address that. So the approach that we propose to solve this problem is a two-stage approach. First, we propose to detect the regions where the activity is happening, and this is our localization network. And once we detect the regions where the activity is happening, we get the video from that region and classify what activity is happening. That's our classification network. So the network that we propose is an encoder-decoder architecture, and we avoid using the region proposals, and we do detection of these activity regions at a video level rather than doing at object level and having to address the problem of merging them. And finally, we use RGB videos to train our models, and we don't rely on any other modalities. So here is the overview of our network architecture. Let me walk you through this network architecture. So we are given a long untrimmed video. We first divide this into non-overlapping clips, and each of the clip we pass through our localization network. So the localization network, as I was mentioning, is an encoder-decoder network architecture with the skip connections and at rest convolutions, and we do this multi-scale features as well to get better performance. So the output from the localization network is a binary mask telling us where the activity is happening. So if the activity is happening, then we have 1, and if there is no activity, there is 0. So given this output from the localization, given this localization mask as an output from the localization network, we crop the regions where the activities are happening, and we pass these we call these as the clips, and we pass these extracted, we call this as tubelets, and we pass these extracted tubelets to our classification network. So the classification network will classify the action that is happening in each of these tubelets. Once we have the predictions for each of the tubelets, actually we do this for all the clips that we have in the video. So we have a bunch of predictions for each of the clips. So then the post-processing system we propose is the TMAS system. So this TMAS system merges and splits these actions based on the based on the predictions from the classification network, and builds these activity tubelets. So these activity tubelets are the final predictions from our network, which tells us where the activity is happening and from what timestamp to what timestamp the activity is occurring. So coming to the results or the visualization of the visualization from the localization network, here I'm showing the binary mask that we get from our localization network. So as you see, the network tries to predict where the activity is happening, and you see the mask actually tracking the car here. Here is another example. So initially when there is no action, there is no prediction, but as soon as someone appears in the scene and then they start walking, the network is able to predict the region where the activity is happening. So to get good performance, good localization performance from the localization network, we have to address this problem that we have with scale imbalance. So what I mean by that is that if you look at the example here, we have a large field of view, and the region where the activity is happening can be very small. You see the person, the pixels occupied by the person are too small compared to the entirety of the frame. So we need to get good localization. We need to handle this. So one way to handle this is using a dice loss. So what dice loss does is that it will handle this imbalance in a pixel-wise classification setup, and it focuses on more on the ratio of foreground and background regions. So we take this dice loss and extend and propose this patch dice loss. So what we mean by that is that in the generalized dice loss, the dice loss is computed on on individual pixels. So if we have n pixels in our frame, we are computing this dice loss using this formulation. So basically, it's 1 minus twice the intersection over the union, where the intersection and over union is computed between the predictions and the ground truth. So we extend this generalized dice loss to the patch dice loss. The way that we do it is that given an input frame, we divide the input frame into k patches. In each patch, if there are m pixels, then we are computing the dice loss on each of the patch and averaging the losses of across patches. We further extend this patch dice loss to do multi-scale patch dice loss. What I mean by that is that instead of, so to do the patch dice loss, we have to specify the size of the patch. So in the multi-scale patch dice loss, we compute the loss at different scales, that is different patch sizes, 3 by 3, 5 by 5, 7 by 7, so on. So this actually helps us detect smaller objects as well. So this multi-scale loss is helping us to detect smaller objects. So the final loss is the combination of these individual patch dice losses at different scales. And coming to the results from our the final results. So here we are visualizing the activity tubelets. So each of the bounding boxes corresponds to an action instance, and the color shows the class of action. So our network is able to correctly predict the temporal extents as well as the locations where the activities are happening. Here is one more example. Uh, Here is one more example. If you see here, as the vehicle starts moving, you don't see the vehicle initially, but the network, even though there is occlusion, can recognize that vehicle and classify the action there correctly as vehicle turning right. So coming to the evaluation of the system, we evaluate the performance of our system on this pretty big data set called NEVA. And here we are comparing the performance of our system with the previous or the other works which have shown results on this data set. On the x-axis, we are showing the processing time, that is how at what speed we are able to process the videos. And on the y-axis, we are showing the AUDC score, which is the error rate actually. So ideal system should have low error rate, and we should also have low processing time. So we want the system closer to the origin, and we show that our system is comparatively better than all the others on both the metrics. here are the actual numbers. So we both AUDC and PMS, the lower is better, and we get lower performance than the other. And for processing time, the higher is the lower is better. So here we're showing the processing time with respect to the number of the time taken. So it's only 0.3 seconds to process a video. So to summarize, we have introduced Gabriela, a real-time system for spatiotemporal action detection and surveillance videos, and this system can run at thrice the speed of thrice real time. That is, if usually the videos are itself at 30 FPS, so we can process it at around 100 FPS. And the different components of the system are the action localization network, which is trained using novel passed laws and which can detect the objects of varying scales. And the next component is action classification network. And finally, the tubelet merging and splitting algorithm that we proposed as a post-processing to get the final predictions. And to highlight, this paper got the best paper award in ICPR 2020. So yeah, so the chapter that we looked at currently just now is on activity detection, and it was addressing the aspect of where. So the final chapter will be on the work which we did on action biometrics, which is addressing the aspect of who. So this work titled W2 Disentangled Feature Learning to Classify Who is Doing What in Actions is currently under submission. And the problem that we are trying to solve here is the action biometrics. And to motivate why we need this, so consider traditional approaches for biometric identification. So here are the traditional approaches. Either we use fingerprints, face recognition, person re-ID, or gait recognition. But each of them has its own constraints. For example, for face and person re-ID and gait recognition, you assume that for face is visible for face recognition, and for person re-ID, either the person should be standing, and for gait recognition, the person should be walking. So these are the constraints with the traditional approaches for biometric identification in images and videos. And what we want to propose is a generalized approach for the biometric identification in videos. So this has applications in many domains, such as elderly care, sports analysis, and video tagging. So if you, for example, for sports analysis, if you know which player is doing which action, that can help in coaching and so on. So here is the proposed, let me talk about the proposed solution for here. So the idea is that we want to do this, solve the task of action biometrics, where we want to recognize the action irrespective of we want to recognize subject irrespective of the action that they are performing. So just to reiterate, this is an example that I showed you earlier. So here on the left, we have a probe, which is for subject P001, and she's drinking water. But given this video, we want to retrieve the videos of the same subject, irrespective of the actions that she's performing. Yeah, so what we propose is that we propose this disentangled representation learning, which is similar to the first work that we have done. And our proposed solution solves this problem and addresses the aspect of both what and who. So here is the network architecture. Again, I will go through individual steps. So here we start at training time. We start with processing 3 different videos: the anchor, same action, and same actor. That is for the actor and same act, the anchor and same actor, or 2 videos of the same actor, and the anchor and same action, or 2 videos of the same action but different actors. So we pass these three videos through a spatiotemporal encoder to get the temporal features, and we add the positional encoding to these features and pass them through our 2 branches of transformer decoders. So compared to the first chapter where we use a similar architecture, here we have 2 different branches, one for action classification and one for the actor classification. So the reason that we do this is that here in the first work, we had only 1 query feature. So we just combined that with the additional view features, and then we were able to, additional action features, and we were able to train. But here, because we have multiple action features and multiple actor features that we want to learn, we introduce these 2 different two decoder branches. So the first branch that we have is the actor branch, where we pass in the input from the videos, and we have learnable action queries that comes as an additional input and gives us the refined actor queries. The second branch that we have is the action branch, and here we pass in the input along with the learnable action queries, and the output is the refined action queries. So these outputs from both the branches are passed through two different MLP layers to classify the actor and action in these videos. And we use the classification loss for the actor classification loss and action classification loss for the both branches to train them. In addition to this, we also add the contrastive losses, which we have seen in the first work as well. Here, in the contrastive loss for the actor, we want to pull together the features of two different videos if they are of the same actor and irrespective of the action. And in the other contrastive loss, we want to pull together two features of two samples if they are of the same action but of different actors. So in addition to these four losses, we also have the orthogonality loss, and we only apply orthogonality loss on the action features uh, because we are interested in getting better performance here. So the final loss is a combination of all of these losses. Now coming to the quantitative results. So we evaluated our system on multiple data sets. So the first data set is what I already talked about, is the NTU RGBD 120 data set. This is one of the biggest data sets, and we compare the performance of our method on both action classification and actor classification. So for actor recognition, the metric is the top one retrieval based score, and for action classification is the accuracy. So we compare the performance of our method with the previous with the baselines when we use I3D, R3D, Vivid, and VideoSwin as baselines. There are no existing works on this task earlier, so we had to come up with our own baselines to show improvement in performance, and we show decent improvements, actually very good improvements on the NTU RGBD. So the next experiment that we show is on the dataset of Toyota smart homes. This is specifically for activities of daily living for elderly care, and we show that we also get good performance on that. So the next dataset is a PKUMD dataset, which is a smaller dataset compared to the NTU RGBD. And then we also show results on SIMS4 action dataset, which is a synthetic dataset. And here the videos were collected using a game engine, and then we also showed results on that dataset. And finally, we also show results on this Accenture MM1 activity dataset, which is an outdoor dataset. So all the others are indoor, but this one is an outdoor dataset where people are doing outdoor activities, and still we get good performance on that. Coming to the qualitative results, here I'm showing you a sample of a person doing action, and the subject ID is P001, and he is drinking water, or she is drinking water. If we do retrieval based on the features for this, what we observe is that we are able to retrieve the videos of the same subject doing different actions. Here is another example where the subject is P003, and we are able to retrieve videos of him doing different actions. So here, some of the actions, for example, wipe face, the face is not visible at all, but we are still able to retrieve that video that shows that to solve this problem, we are not just looking at faces and solving it. Here is another example of person 007, and we are again showing the same example of retrieving other videos. So to summarize, we have proposed the network architecture called W2, which is a novel approach to solve the problem of joint actor identification and action classification. And this achieves improved performance over all the baselines on all different data sets. We do experimental evaluation thoroughly on 5 different data sets, including both indoor, outdoor, as well as synthetic data set. And yeah, so that's the end of this chapter, where we talked about this joint actor and action recognition, which addresses the aspect of action biometrics. So here is the outline that I showed you earlier. So these are the 4 different works that I talked about, and each of them. So the first we discussed about multi-view action recognition addressing what. Then we discussed about multi-label temporal action localization addressing when, and then we discussed the action detection system that we developed addressing where, and finally I presented to you our work on action biometrics addressing the concept of who. So to summarize, the first work on multi-label action recognition learns view invariant representations to solve the problem of multi-view action recognition using feature disentanglement, and we achieve state-of-the-art results. In the second work on multi-label temporal action localization, we learn the co-occurrence and temporal dependencies to solve this problem, and we show competitive performance and also interpretability. And in the third work, we talked about the system on real-time action detection. We propose a two-stage approach for localization and classification, and we show that our system can do the spatial temporal action detection in this large field of view surveillance videos at a high speed, that is 100 frames per second. And the last work is on joint actor identification and action classification, where we again leverage the idea of disentangled representation learning and showed improvement over the baselines. So finally, coming to the future work, one direction of future work for multi-view action recognition is that we can explore the idea of pseudo labeling to reduce annotation costs here. And other direction is we want to improve the generalization to novel views. So we want to see how we can improve the performance in that aspect. And looking at multi-view temporal action localization, one direction is that we want to optimize the network to process longer sequences. So the network that we have used is a transformer-based architecture. And if the length of the input increases with transformers, the memory requirements also increase. So that could be one direction. And the other direction is that if we want to localize fine-grained actions, which are very, which can be very short, then it would be hard to localize them. So one extension could be to address that problem. And and the other direction for the joint actor identification action classification is that there are no large scale data sets to evaluate on this task. And so we had to reuse the existing data set. So one direction could be to build this large scale data set, which will encourage development of methods and their benchmarking. And finally, the one other direction is that I have talked about the different aspects of what, when, where, and who, and different systems for each of that. But one future direction could be build an end-to-end system which unifies all of this and can solve all the four tasks in a single approach. And here are my selected publications. We have published in AAAI, CVPR, ICPR, ACM Multimedia, and we also have one patent. And thank you so much.